work on the worksheet that I gave you last time. So the first question says that state the speed at which all electromagnetic waves travel in vacuum, and it's all the same speed. It's just 3 times 10 to the power of 8 meters per second. State which of the components shown has the lowest frequency. So the lowest frequency is radio waves, all right, and the highest frequency is gamma rays. 2 components are not listed above. State the names of these components. So X-rays are not listed, and infrared is not listed as well. So these are the 2 components that are not listed. Going to microwaves, and this question number B suggests one reason why it is sensible to prevent microwaves from escaping. Because they are harmful to living tissue. All right, that's why we don't want them to escape. State one further application of microwaves other than the microwave ovens in satellite phone communication. All right. Now this is the first page, and let's move on to the next part. Now in the next part it says that for blue light the refractive index is 1.5. Calculate the critical angle of blue light, and let me go down a little bit. The critical angle sine C equals to 1 over n. C is equal to sine inverse of 1 over 1.5, and 1.5 is that refractive index. I don't have my calculator near me right now, but the answer is 41.8 degrees. Remember that angles needs to be given correct to 1 decimal place. Moving on to the next question, it says that at P some of the light is refractive and some of the light is reflective. The blue light is used in this experiment is monochromatic. State in terms of measurable quantity what is meant by monochromatic. So monochromatic is a light with a single wavelength. Okay, we say wavelength because wavelength is a measurable quantity. We can say frequency, but we cannot say color. Okay, but calculate the angle of refraction of the light in the block. So we have the angle of incidence is 45 degrees, and we want the angle of refraction. And they already gave us the refractive index, which is 1.5. So I can use, if light is going from if it's less dense to more dense, okay? And I don't want you to write this in your answers, but if it's going from less dense to more dense, an easier way to do this is to say n equals to sine I over sine R. That's one way. But if you want to do it the other way that we used to do it, you say n1 sine theta 1 equals to n2 sine theta 2. And that's another way. I don't know if I confused you, but try to keep up. n1 is air, so it's 1. Sine 45 equals to 1.5 sine R. Sine R is equal to sine 45 over 1.5, and R is equal to sine inverse of that. R is equal to sine inverse of sine 45 over 1.5. Okay, and again, I don't have a calculator. Just plug in this in your calculator and you get your final answer. Now, the last question says that draw the path taken by the light that is reflected into, draw the light into the block and the one is reflected back. So to draw the one which is reflected without calculation, you use angle of incidence equals to angle of reflection. So this needs to be 45 as well. Looks like a 45 to me. And if light is traveling from a less dense to a more dense, it refracts towards the normal. I know, I always tell you don't use pens to draw, but sorry for that. Moving on to the next question. On figure 8.1, cross out the wrong and correct them. So ultrasound is wrong. Instead of it, it's ultraviolet. Okay? And for the second one, earthquake is wrong. Instead of it is radio waves. Again, electromagnetic spectrum. The speed of light in vacuum is 3 times 10 to the power of 8 meters per second. And the refractive index, we can calculate that by velocity in air over velocity in medium. Velocity in air is 3 times 10 to the power of 8. The velocity in the medium is here, which is 2 times 10 to the power of 8. We cancel that, it's a 1.5. The critical angle, again, sine C equals to 1 over 1.5. C is equal to sine inverse of 1 over 1.5, and this is 41.8 again. Okay? After that, state the full name of this effect. This full name is called total internal reflection. That's the full name of it. And going down to this, it's called a periscope, guys. And in a periscope, light enters without bending. It reaches here, it totally internally reflects. And when it reaches here, we need to draw another prism so that it totally internally reflects again. So your prism is going to look like that. So it enters, it reaches here, and it totally internally reflects. And this is a periscope. It's used in submarines. It's used to view something at the top while you're at the bottom. Okay? And this is it for this question. Now, B, select the statement that is correct. Describe necessary conditions to undergo total internal reflection. The angle of incidence is greater than the critical angle. The speed of light in glass is less than the speed of light in air. These are the two conditions. Okay? Moving on, explain what is total internal reflection. This is when all the light reflects back into the same medium. Okay, critical angle, the angle of incidence in the denser medium, okay, that produces an angle of refraction of 90 degrees. I think my handwriting is a little bit big, so I need to reduce that. Then we're going to come back to this drawing in a bit, but the speed of light in air is this, the speed of light in glass is this, the refractive index would be speed of light in air over speed of light in glass, and this is 1.5. No unit for refractive index. We call it a dimensionless quantity because both are in meters per second and they both cancel out. Show that the critical angle for the glass air boundary is 42. It's the same. Sine C equals to 1 over 1.5. Okay, sorry, back to it. C is equal to sine inverse of 1 over 1.5, which is a 41.8, which is approximately 42 degrees. Now on figure 7.1, carefully draw the continuation of the path. Back to the diagram here. To show the continuation, the ray goes directly over here. It doesn't bend because it's perpendicular to the surface. Okay, it doesn't bend. Now when it reaches here, you have to draw a normal. Okay, when you draw a normal, it has to reflect back because the angle of incidence is greater than the critical angle. This angle is 60 degrees, while the critical angle C is 42 degrees. How did I get 60? That's a 90, that's a 30, but we don't need to calculate all that. And after it reaches here, because it's going from a denser to a less dense, it refracts away from the normal. This time it refracts away from the normal because this angle is 30 degrees, which is less than the critical angle. So it's all about critical angle and total internal reflection. Hope that you understood this part. Question number 5 says that A, B, C, D. So A is it's infrared. B is ultraviolet. C is X-rays. D is gamma rays. Okay? Moving on. The second question is about dispersion of light. So calculate the angle of refraction. So I have this, I have this. So I'm going to say N1 sine theta 1 equals to N2 sine theta 2. N1 is air, sine 35 equals to 1.5 sine R. R is equal to sine inverse of sine 35 over 1.5, and you use your calculator for that. On figure 6.2, draw the refracted ray at phase xy. So refraction is going to be towards the normal, so it's going to be something like that. Emerging away from side xz. So when it emerges away from side xz, you have to draw another normal, okay, and it refracts away from the normal like that. Okay? A ray of blue light, so you need to draw another ray, but this time it refracts a little bit more because of its, I'm going to exaggerate the refraction here, and over here it also refracts away from the normal. So the first one was red. Okay, so this is the red and this is the blue, and the blue refracts more than the red. Remember that dispersion takes place because light with different wavelengths and different colors travels at different speeds and refracts at different angles. The refractive index, again, in this glass block, so refractive index is going to be 3 times 10 to the power of 8 divided by 1.9 times 10 to the power of 8. So 3 over 1.9 is going to give you approximately approximately 1.5 something. So I'm just going to write it as 1.5 without a unit. Okay, now coming to this next question, which is a question about lenses. We don't have the lens drawn for us, and the first question says that on figure 8.1, draw a straight line to represent a ray from the tip of the arrowhead to the tip of the arrowhead of the image. So I'm going to bring this. Okay, people, I have to, from the tip to the tip, I need to be very accurate here. Tip, and I'm using a pen so I cannot make any mistake. Tip to tip. That's a straight line from tip to tip. Now, this dotted line must extend above and below, so we need to indicate the position of the lens. And remember, the lens would be here in this position. So this is going to be my lens. Why is it my lens here? Let me just try to draw it a little bit clearer. Okay, so if you can't see it, that's going to be my lens, people. Okay, it's here because this is the center of my lens. Okay, why is it? Remember, the ray that goes from the tip passes through the center, reaches the image. This ray passes through the center of the lens. That's why this line is my lens. Draw a second ray from the tip to indicate the principal focus. So the second ray always goes parallel. Okay, goes parallel. Can you see that? It goes parallel like this. And from here, it goes and converges to the image. So from here to here, it converges to the image. Okay, and this point here is going to be F. Okay, I don't know if you can see that properly, but I'm going to do this. Maybe it can indicate things a little bit clearer, and I hope that it's clear. Now, if I want the focal length, I'm going to use this 1, 2, 3, 4, 5 is 1 centimeter. So 1, 2, 3, 4, 5, 1. 1, 2, 3, 4, 5, 2 centimeters. 1, 2, 3. So I think it's 2.6 centimeters, okay? Because each one is going to be 0.2. So 2.6 centimeters would be your focal length. Remember, the focal length is from here to here, from the center to F. Okay, people, center to F. Moving on, turning the light back again. So image I has described as enlarged and inverted. State and explain one other characteristic. So my statement would be it's real. Why? Rays of light intersect to form image. Okay, now shows a spherical fishbowl full of water by window. Black curtain hangs behind fishbowl. When a full water is fishbowl acts as a converging lens. Suggest one possible hazard. Leaving the fishbowl next to the window in bright sunlight, it might cause a fire. Don't explain, just a suggestion. How can it cause a fire? Because it's going to focus the rays on one point, and this might lead to the black curtain heating up and catching fire. Okay, question number 7. A ray of light in air is incident on a glass block. The light changes direction. State the name of this effect. Refraction. The cause of this effect, change in speed of light. Okay? Going to this, again, we're going to turn this off because we can actually see clearer like that. On figure 8, mark each of the 2 principal focuses and label them with F. So the principal focus needs to be 3.5 centimeters. 3.5 centimeters, let me start counting. 1, 2, 3, 4, 1, 2, 4, 5, 3, 1, 2, okay, that's one principal focus, 3.5. Okay, so here on the other side, 1, 2, 3, 4, 5, 1, 2, 3, 3.5 is over here. So you have to mark them. And I hope that you can see clearly. So I marked 1 point here and 1 point here. So I'm going to turn it off again. Now draw and label the image. Remember, the first line goes directly through the center. So it goes directly through the center like this. That's your first ray. You see that? The second ray goes from the tip to the lens, parallel. Okay? When it reaches the lens, it converges and passes through F. So it converges and passes through F like that. Where the 2 rays meet, I think they meet up here. So where the 2 rays meet, you have to draw your image. Looks something like that. Okay, and that's going to be my image. If you can't see it properly, I'm going to stress on this line a little bit so that you can see it properly. Okay, that's my image. Okay, back to the question. Height of the image, so 2, 3, 4, 5, 1, 2, 3, okay, let's say 4 centimeters according to what I did. If you found a different answer, that's totally fine as well. So moving on. Okay, in this question, light. Explain why the light does not change direction as it enters the block at F. Because the ray is perpendicular to the surface. The refractive index of glass is 1.5. Calculate the angle between the normal and the ray after it emerges. So the ray after it emerges would do something like that, away from the normal, right? This is how it's going to look like, and this is the R that you're trying to find. Now remember, it's moving from glass to air. So when you use the rule, N1 sine theta 1 equals to N2 sine theta 2. N1 would be glass, because it's in glass right now. So 1.5 sine 30 equals to air sine R. R is equal to sine inverse of 1.5 sine 30. Again, don't have a calculator, so just put it in your calculator and find it. It sketched the path of the light that emerges. So the path of the light that emerges is going to be the one that I drew at the top here. Okay? Moving on. The direction of light striking the curved surface of the glass block chain, the angle between the ray and the normal at Q gradually increases from 30 to 90. Describe, look at this term, describe what you see. What happens to the light that strikes the block at Q as this angle increases. 1. The angle of refraction will increase. Okay? When the angle of incidence reaches 90 degrees, the angle when the angle of incidence reaches, this is how you fix the mistakes you did, reaches the critical angle, the angle of refraction will be 90 degrees. When the angle exceeds the critical angle, total internal reflection takes place. Okay? Alright guys, so question number 9. I hope that we're almost there. So the speed of light in air is this. Calculate the refractive index. I'm not going to do that because I've done it again and again and again. The angle of incidence is 40 degrees. We want the angle of refraction. So the angle of refraction again, N1 sine theta 1 equals to N2 sine theta 2. N1 is air. Sine 40 equals to 1.5 sine R. Okay, so again, you just do the same thing, okay, as we used to do. The next question is about real and apparent depth. So to find the position of the image, what you need to do, you need to draw 2 rays. The first ray is going to go directly to the outside. Okay, that's my first ray. The second ray, okay, how can I do that? Now the second ray goes from the eye, okay, directly to the water. But when it reaches the water, it bends. It bends like that. Now, where you see the image is going to be just a continuation of this. So you continue this with a dotted line, because it's imaginary, and that's going to be your position of your image. That's why when you put a coin in water, you see that the coin actually looks bigger, or the coin actually looks shallower. Okay? Moving on. State what happens when the angle is less than the critical angle, so refraction. Greater than the critical angle, total internal reflection. Okay? Now, let's look at this. On figure 6.1, continue the path. So when I continue the path, the critical angle is 41. When I draw a normal, this angle is 60. It's greater than 41. That's why total internal reflection would take place. Okay? But when it reaches this, it would refract away from the normal. Okay? Calculate the refractive index. If I was given the critical angle, refractive index is 1 over sine C, which is 1 over sine. The critical angle is 41. So you just put that in your calculator and you get your answer for the refractive index. People, that's a very long worksheet. I don't know how I gave you this worksheet. It's very long. Okay, moving on. Now, light is traveling on an optical fiber. Explain why the quantity refractive index does not have a unit. Because it is the ratio of the speeds and the units cancel each other. Alright? Calculate the speed of light in glass. So if I have the refractive index, the speed of light in air is 3 times 10 to the power of 8 over v. v is equal to 3 times 10 to the power of 8 over 1.5, which is 2 times 10 to the power of 8 meters per second. Describe one use of optical fibers in communication technology. It is used to transmit signals. Okay, you can say, for example, internet. Okay, how does it do that? The pulse enters the fiber and undergoes total internal reflection and until it reaches the receiver. The pulse can be in the form of light or infrared. Good. Okay, so figure 7.1 shows a converging lens and its principal axis. So on figure, draw 2 rays from the top to locate the image. Remember, the first ray always passes through the center of the lens. Okay, center of the lens. The second ray goes parallel and then passes through F. Passes through where? Sorry guys, I got carried away. Passes through F. You realize that the rays, they're not meeting. So we have to extend them backwards. And this is the use of the lens as a magnifying glass. People, you also have to practice the drawing of images of diverging lenses, not just converging lenses. So where the rays meet, you draw your image. So the image is going to be up here. Now, the second one, the object, the image. Figure 7.2. Underline 3 of the terms below to describe the image on figure 7.2. 7.2 is this. The image is real, inverted, enlarged. That's it. Alright? Last but not least is blue light enters the prism. Draw the path of the blue light. So yellow light enters, blue light is refracted a little bit more. People, I started becoming careless a little bit because it's the last question. And it goes like this. Alright, and people, thank you very much. That's it. We're done.